Hello everyone. So by now we have gone through all the four different methods of solving a pair of linear equations in two variables, right? So we've seen the graphical method, then we have moved on to the algebraic methods, right? In the algebraic methods, we saw the method of substitution, saw the method of elimination, and we have seen the method of cross multiplication, right? Now let's move on and study about the conditions for solvability or consistency of the pair of a linear equation in two variables. So earlier in the chapter, we saw three different situations that might happen with a pair of linear equations when we represent them in graphs, right? So the first situation was where the two different lines, which were represented by the two different linear equations in two variables, intersected at only one single point, right? So this was one of the conditions. In other terms, we can also say that in this particular situation, the pair of linear equations have exactly one solution, right? Why? Because any solution of a pair of linear equations is the point, right, which is a solution for the first equation as well as the second equation. In other words, it is a point which lies on one of the lines and on the other line as well. So in this particular situation, we see that there is only one point at which these two lines intersect, right? So this point is a unique solution for this pair of linear equations in two variables. So this is the first case that we'll study about, right, where we get a unique solution for the pair of linear equations in two variables. Now in the next case, we saw that there are two lines which were actually parallel, right? So we had a pair of linear equations which when we represented on a graph, we actually got a pair of parallel lines. Now in this situation, we can clearly see that there is no solution that exists for this pair of linear equations in two variables, right? Because these two lines, which are again the graphical representations of the linear equations only, these two lines, they do not intersect at any point, right? Or in other words, there is no point or there is no solution which lies on both of the lines, right? So this is a situation where the pair of linear equations in two variables actually has no solution, right? And the third case that we saw was where both the lines were coincident, right? Both the lines were actually coincident. So when we plotted the pair of linear equations on a graph, we got two lines which are coincident, right? So now in this particular situation, we can see that every point which lies on any one of the lines also lies on the other line as well, right? In other terms, any solution of one of the equations is also a solution for the second equation, right? So these pair of lines have infinitely many solutions, right? Why? Because all the points which lie on the first line also lie on the second line, right? So all the solutions which are there of the first linear equation are also solutions of the second linear equation. So this pair of linear equations has infinitely many solutions, right? So these are the three cases that we have that we'll study in a little more depth now, right? The first situation is where we have a unique solution for a pair of linear equations. The second situation is where we have parallel lines, right? Or we have no solution for the given pair of linear equations. And the third situation is where we have coincident lines, right? Or where the pair of linear equations in two variables actually have infinitely many solutions, right? So let's start with the case one, right? So in case one, we get a unique solution, right? So in this case, we have two lines which actually intersect on a single point. Now in the method of cross multiplication, we saw that for a general form of a pair of linear equations, this is how we can find the values of x and y, right, using this particular formula. So if I write the values of x from this formula, I get the values of x as b1c2 minus b2c1 upon a1b2 minus b1a2, right? So from that formula, I can calculate the value of x, right? And from that formula, I can calculate the value of y as well, right? So the value of y comes out to be c1a2 minus c2a1 upon a1b2 minus a2b1, right? So for those pair of linear equations in two variables, right, for any general form of pair of linear equations in two variables, the value of x can be given by b1c2 minus b2c1 upon a1b2 minus b1a2, right? And the value of y can be given by c1a2 minus c2a1 upon a1b2 minus a2b1. Now for this to be true, we saw one very important condition, right? That important condition was that the denominator that we have here, right? The denominator that we have here should not be 0, right? Because if this denominator is 0, we would not be able to calculate the values of x and y, right? Because something divided by 0 would be not defined. So, from this thing, we can write the condition a1 b2 minus b1 a2 should not be equal to 0, right? Because if this is equals to 0, we would not be able to calculate the values of x and y. So for this to be true, I can rewrite this as, so if I divide this equation by a2 b2, I get the value as a1 upon a2 minus b1 upon b2 should not be equals to 0, right? So if I divide this equation by a2 b2. So this is the condition that we get, right? So if I rearrange this, I get the situation a1 upon a2 should not be equal to b1 upon b2. Right? In other words, I can say if this condition is true, then there is a unique value of x that exists, right, for the given pair of linear equations in two variables. And if this condition is true, there is a unique value that exists for y, right, for the given pair of linear equations in two variables. So I can, in other terms, I can say that if this condition is true, we get a unique solution, right, a unique pair of x and y, a unique solution which exists for the general form of linear equations in two variables. So for the two lines that can be represented by the pair of linear equations to be intersecting at only one single point, right, which gives us a unique solution, this condition has to be true, right? So we can use it in both ways. So if we know that this condition is true, we can say that the pair of lines, pair of linear equations in two variables actually have a unique solution, right, or they intersect at only single point. On the other hand, we can also say that if we know that there are a pair of linear equations in two variables which intersect at only one single point, right, or which we know that has a unique solution, we can say that this condition is going to stand true, right? So this is the condition for consistency of a pair of linear equations in two variables, right? Or in other terms, this is the condition which has to be true for the solvability, or for us to be able to solve a pair of linear equations to get a unique solution. So this is the first case that we have analyzed, and we have found out a condition for that first case to be true. So we have seen the first case in which a pair of linear equations in two variables has a unique solution, right? So now for a pair of linear equations to have a unique solution, we know that the condition a1 upon a2 is not equal to b1 upon b2 should stand true, right? So this condition for the coefficients of the pair of linear equations should stand true for the pair of linear equations to have a unique solution. Now let's move on to new cases. So now for this case, we had assumed that a1 b2 minus a2 b1 should not be equal to 0, right? Because if a1 b2 minus a2 b1 was equals to 0, we would not be able to calculate a solution to that system, right? So let's assume that a1 b2 minus a2 b1 is equals to 0, right? So we've already seen the case where we have taken this to be not 0, right? In that case, we get the pair of linear equations to have a unique solution. So now let's take this case and see what we get. What result do we get from taking this particular condition to be true? So this I can rearrange to get the value a1 upon a2 is equals to b1 upon b2, right? So if I rearrange this, I get the value a1 upon a2 is equals to b1 upon b2. Now let's assume this value to be k, right? So we have assumed that instead of this condition being not true, this condition is true, right? From that we got the expression a1 upon a2 is equals to b1 upon b2, which we have equated to some value k, right? So now let's take the pair of linear equations in two variables. So the pair of linear equations in two variables that we have are a1x plus b1y plus c1 is equals to 0, right? And a2x plus b2y plus c2 is equals to 0. We know that this is the general form of a pair of linear equations in two variables, right? So now in this equation, can we use this particular inequality to represent any one of the equations in terms of the other equation? Well, for this I can rewrite, using this equality, I can rewrite A1 as A2k, right? And I can rewrite B1 as B2k. So I can rewrite the coefficient A1 in terms of the coefficient A2 and the coefficient B1 in terms of the coefficient B2. So now if these two values, if I put in the first equation, so if I put these two values in the first equation, I can rewrite the first equation as A2k x plus B2ky plus C1 is equals to 0. Or I can rewrite this as A2x, right? I've taken k common from these two values, A2x plus B2y plus C1 is equals to 0. Right? So this is how I can represent the first equation, right? So this is one more representation of the first equation only. This is just the first equation, right? So using this particular equality, we have represented the first equation in terms of A2 and B2. Now from this equation, I can clearly see that the value of A2x plus B2y, I can calculate from this equation, right? So I can calculate the values of A2x and B2y from this particular equation and I can put that value here. So let's assume that the equation 2 has a solution, any arbitrary solution alpha comma beta, right? So for some value alpha, which is the value of x, and some value beta, which is the value of y, this equation becomes 0, right? Or in other terms, this is a point alpha comma beta which lies on the line A2x plus B2y plus C2. So given that this is a solution, any arbitrary solution for this equation, let's figure out if this solution is also a solution for the equation 1 or if this solution is not a solution for the equation 1. So now for this solution to be a solution of equation 2, I can rewrite equation 2 as A2 alpha plus B2 beta plus C2 is equals to 0, right? Or I can say A2 alpha plus B2 beta is equals to minus C2, right? So saying that alpha comma beta is a solution to the equation 2, we have derived this particular condition, right? Where alpha and beta is any arbitrary solution which is a solution of the second equation. Now let's see if alpha comma beta is also a solution to the equation 1, right? So if I put the values of alpha comma beta here, I get k into A2 times alpha plus B2 times beta plus C1 is equals to 0, right? But I know that the value A2 alpha plus B2 beta can be represented as minus C2, right? So I can substitute the value minus C2 into the equation 1 to get k times minus C2 plus C1 is equals to 0, right? So I can also represent this as C1 is equals to KC2. So now if this condition is true, if this condition C1 is equals to KC2 is true, then the solution alpha comma beta will also be a solution to the equation 1, right? If this condition is true, the solution alpha comma beta, which was a solution to the second equation, will also be a solution to the first equation, right? So if this condition is true, all solutions alpha comma beta, any arbitrary solution alpha comma beta which is a solution of the second equation will be a solution of the first equation as well. So this will be a solution of equation 1 and equation 2. In other terms, I can also say that all the points alpha comma beta which exist on the line A2x plus B2y plus C2 is equals to 0. In other terms, all the solutions of this equation will also be a solutions of the first equation. So all the points alpha comma beta which lie on the second line will also lie on the first line. So if this condition is true, what we get is a pair of coincident lines. right? Or we can also say that this is the case for this pair of linear equations to have infinitely many solutions, right? But what if this condition is not true? What if C1 is not equals to KC2? If C1 is not equals to KC2, then for any value, any solution alpha comma beta, which is a solution of the second equation, this equality is never going to be true, right? So we'll never get any alpha comma beta to be a solution of the first equation as well, right? So if this condition is true, any solution alpha comma beta of equation 2 is not going to be a solution of equation 1. Right? Any arbitrary solution alpha comma beta of equation 2 can never be a solution of equation 1 if C1 is not equals to KC2. So now from this we have derived two different values, right? So two different conditions. So where C1 is equals to KC2, where we get a pair of coincident lines, right? Or where we get the pair of linear equations to have infinitely many solutions, because every solution of the second equation also turns out to be a solution of the first equation. And in the case where C1 is not equals to KC2, we get alpha comma beta, which is an arbitrary solution of the equation 2, to never satisfy the equation 1, right? Or we can also say that this pair of linear equations has no solution at all. There's no common point at which both these lines will intersect. So we can also say that this will lead to a pair of parallel lines, or a no solution situation for the pair of linear equations in two variables. So now I can rewrite this condition in two ways, right? So if A1 upon A2 is equals to B1 upon B2 is equals to K, right? K is the value C1 upon C2. So if it is equals to K, which is C1 upon C2, then I can see that the equation, the pair of linear equations are actually coincident lines, right? Or this pair of linear equations have infinitely many solutions, right? But in the other situation where A1 upon A2 is equals to B1 upon B2, right? And from this equation we get C1 upon C2 is not equals to K, right? Or in other terms we can write A1 upon A2 is equals to B1 upon B2 is not equals to C1 upon C2. So in this condition, what we'll get a pair of parallel lines, right? Because any solution to the equation 2 is never going to be a solution to the equation 1. So if this condition is true, we get a pair of coincident lines, right? Or we say that the pair of linear equations have infinitely many solutions. And if this condition is true, we can safely say that the pair of lines that we have got are parallel lines, right? Or the system of linear equations has no solution at all. So now we have seen three different cases, right? So for a general pair of linear equations in two variables, we have seen three different cases that occur. So the first case is where we get a unique solution for the pair of linear equations in two variables, right? So in this case, we get two lines which intersect at only one single point. And also in this case, we figured out that the relationship that exists between the coefficients of this pair of linear equations in two variables is A1 upon A2 should not be equal to B1 upon B2. In other words, we can also say that if A1 upon A2 is not equals to B1 upon B2, we can safely say that the given pair of linear equations in two variables is actually going to have a unique solution, or these two lines are going to intersect at only one single point. The second case that we saw was where a pair of linear equations, we saw that with the general form of pair of linear equations. So a pair of linear equations has infinitely many solutions, right? So in this particular case, we can see that the two lines which can be represented in the graphical form for the pair of linear equations actually are coincident lines, right? And the condition that exists between the coefficients of the pair of linear equations is A1 upon A2 is equals to B1 upon B2 is also equals to C1 upon C2. Or in other words, we can say that if this condition stands true, A1 upon A2 is equals to B1 upon B2 is equals to C1 upon C2, we will get a pair of linear equations which actually have infinitely many solutions, right? Or if represented on a graph, we'll get a pair of lines which are coincident lines. And in the third case, what we saw was where the given system of linear equations has actually no solution at all, right? So we cannot find any point which lies on both the lines, right? Or in other words, the lines are parallel. So the condition which stands true for this to happen between the coefficients of the pair of linear equations in two variables is a1 upon a2 is equals to b1 upon b2, but it is not equals to c1 upon c2. Or in other words, we can also say that if that condition stands true, a1 upon a2 is equals to b1 upon b2 is not equals to c1 upon c2, we'll get a pair of linear equations which actually have no solution at all, right? Or if we represent this pair of linear equation on a graph, we'll get two lines which are actually parallel. So these are the three cases and these are the three relationships that the coefficients of pair of linear equations have to the solvability or the consistency of the pair of linear equations or the system of linear equations in two variables. So this is the basic concept. Now let's move on and apply these concepts on a couple of questions and see how we use this concept.